Hey everybody, Dr. Retzek here with you. Hopefully audio is good on this one. Not sure what happened on the last one. In any case, this is our second video on 15.8. In the first video, we figured out what that area correction factor should be when we change variables in double integrals. And now we want to do a couple of examples. It's one thing to sort of know the formula, and it's another thing to be able to do the problems. So our goal right now is to just do a couple examples. So here's the first one. Example. Let's say you were trying to compute the double integral over some region R of some function with x's and y's in it, done dx dy, and the region was this. So xy plane, and then the region is this. That is our region R. So trying to integrate over this, and it looks pretty bad as far as x's and y's are concerned. I mean, like what's top curve, what's bottom curve, left curve, right curve. There's no good way really to break this up for x's and y's. But in terms of polar, you see, oh yeah, no, this is perfect. So theta equals alpha up to theta equals beta. And let's say this is r equals 1 up to r equals 2. So that region is terrible to describe in x's and y's, but really well suited to a description in r's and thetas. Okay, so what if you said, fine, I don't want to see that region through the lens of x and y. I want to see it through the lens of r and theta. So in our intro discussion, the new variables were u and v. Here, specifically, we've chosen to call the new variables r and theta. And you know that the exchange between x's and y's and r's and thetas goes like this. So x is r cos theta, y is r sine theta, and so the region back here that we were calling G in the intro, so this region is R, the region back here that we're calling G is, well, R's go from 1 to 2, and thetas go from whatever alpha is to whatever beta is. So the region G is very simple. The region G is just a rectangle. And we've been kind of circling around this idea for ages now. You know, when I make jokes about like, oh yeah, but if you put on your polar goggles, well, this isn't some weird shape, this is just a rectangle. Well, now you're really seeing it. Here is the region G. Here is the region G. And so we know from our intro discussion that the integral over r of f of xy dx dy is the same as the integral over g of f of, okay, everywhere you see an x, you put what it is in terms of the new letters. Everywhere you see a y, you put what it is in terms of the new letters. Then you got that Jacobian correction factor. So the symbol for it is dxy dr theta. And then it's with respect to the new letters. Can we figure out what all this is? All right, let's talk about the region G. Well, theta goes alpha to beta, and r goes 1 to 2. Okay, so there's no doubt about that. It's just a rectangle, after all, over in the r theta plane. And then you got your f of r cos theta, r sine theta. So everywhere you see an x, you put r cos theta. Everywhere you see a y, you put r sine theta. Now, let's talk about the correction piece, the Jacobian on this one. So remember, that's just pixels. It's just a shape. It's the notation that stands for this. dx dr dy d theta minus dx d theta dy dr. Now let's think about what all that comes out to. What's dx dr? Well, look. Cos theta. What's dy d theta? R cos theta. So this first piece is r times r cos theta. So r cos squared theta. All right, what's dx d theta? Look back at x. That's negative r sine theta times dy dr. Sine theta and minus minus is plus. So plus r sine squared theta dr d theta. And by trig identity, cos squared plus sine squared equals 1. In the end, simply f of r cos theta, r sine theta, r dr d theta. I don't know if you heard Finn in the background. Even the kids are knowing r dr d theta. They've heard it so many millions of times in the last 3 weeks. So that's the reason there's the r in there. This piece, this is the Jacobian piece for that transformation. So when you see x's and y's through polar, the Jacobian is just r. Great. Okay, so we have confirmation of an old fact. All right, now we got to do a real problem. Okay, so this is the last example of the day, but it's kind of a beast. Okay, in this one, we are being asked to do the following double integral. Compute. Double integral over region R, e raised to the x plus y over x minus y, all done with respect to area, where R is, okay, in the xy plane, here is our region. It's actually down here. So you got -1 and -2, and you got 45s like that. This right here, this is R. Now we had no choice. They just gave us this. This is the region we're supposed to integrate over. So that's 1 and 2. So that's R. Now, let's hit pause. Let's get our bearings. Number 1, whether we do dA in the order dx dy or dy dx, good luck integrating this. Like if x is the variable and y is a constant, I don't know. Or if y is a variable and x is a constant, I don't know, it looks terrible. I don't know how to integrate that. Moreover, even if the thing we were trying to integrate looked manageable, I kind of don't like the region R, right? Like there's no like set left curve or right curve or top curve or bottom curve. At best, this is a break R up into a bunch of simpler pieces and do integrals over each of those pieces kind of situation. I don't know. This just looks doubly bad. The thing looks hard to integrate with respect to x and y, and I don't particularly like that trapezoid R. Okay. The dream is to think up a way to trade in x's and y's for u's and v's in a way that makes the region better and the thing we're trying to integrate better. Okay, so we're trying to dream up some connection between x's and y's and u's and v's. And I'll tell you the main thing that's got me nervous about e raised to all that stuff. It's that the denominator has both variables in it. If that was just an x, well, x plus y over x, that's not that bad. That's 1 plus y over x, and I feel like we could integrate that with respect to y for sure, at least. But the fact that there are x's and y's in the denominator of the exponent is kind of what makes it hard. Now, if you say that to yourself and you say, dang, I wish both letters weren't in that denominator. Well, you could, if you felt like it, say, okay, I'm just going to rename that entire denominator. I'm calling it v. Say, just call it v. So now that denominator is one letter, and that's an upgrade. Well, if we're going to do that, I think maybe why don't we just call the numerator one letter also? Let's get it all like unentangled. Let's just have the denominator be v and the numerator be u. Now, it's fair to ask at this moment, wait, why did you do that? No good reason. You can do whatever you want. Call anything you want u and v. As long as you keep track of things with the Jacobian, you'll be fine. It's just like u sub. You can let u be anything you want. Now, whether it actually turns out in your favor, there's an art form to that. But just look at the thing you're trying to integrate and make a sensible substitution. Now, that looks a little weird because we're used to seeing what x becomes in terms of u and v and what y becomes in terms of u and v. But this relationship, we could write in terms of x equals something and y equals something. Little side project. Off to the side, take this relationship and solve it for x and y. It's two equations and two unknowns after all. So like, what if you added the two equations? If you add them, look what it says. It says u plus v equals 2x. So x is u plus v over 2. Or if you subtracted the bottom equation from the top one, it would say u minus v equals 2y. So if you want the version of the exchange back and forth between old letters and new letters to look like our development, where we had x in terms of new letters and y in terms of new letters, then that's it on this problem. X equals u plus v over 2, y equals u minus v over 2. Okay, now can we talk about the region G? This line right here is on the edge of the region R, and it's a line of slope 1, y-intercept -1. And this line right here is also slope 1, y-intercept -2. So this line is really x minus y equals 1, and this line is really x minus y equals 2, but x minus y is v. And x minus y is v. So everywhere along this top line here on the region R, v is 1. And everywhere along this line, v is 2. So over here, the region G, it must involve v equals 1 and v equals 2. All right, let's find out where this corner is. When x is 1 and y is 0, then look at this box. When x is 1 and y is 0, u is 1 and v is 1. So this dot's cousin over here in the uv land is that dot. Let's find this one. When x is 2 and y is, no, shush. When x is 2 and y is 0, u is 2 and y is 2. So here, similarly, if you find these dots, you will find them over here and over here. Boundary goes to boundary. G is this. That's region G right there. And it's still a trapezoid, but I gotta tell you, what an improvement. It's got a left curve and a right curve. That one looks perfect for, horizontal slices. So the order du dv. All right, so that's G. Okay, last ingredient. Let's figure out that Jacobian. Here we go. If you're interested in the Jacobian in switching x's and y's into u's and v's. Okay, here we go. It's dx du times dy dv minus dx dv times dy du. Let's work this out. Here's the equations right here after all. What do you think? Dx du is a half. Dy dv is minus a half. And multiply those, you get minus a fourth. Take away. Dx dv is a half times dy du is a half. So minus a fourth. So minus a fourth is negative 2/4. That's all in absolute value. So it's a half. Thus, check it out. The original problem over R, e to the x plus y over x minus y done dA is the same as new integral over g e to the, all right, everywhere you see an x, you would put u plus v over 2. Everywhere you see a y, you would put u minus v over 2. When the dust settles, the numerator x plus y, well, you can see it, that's u. Denominator x minus y, that's v. You got the Jacobian piece. That's a half imported from right here. And then you got whatever order you want, area integral in the new G region. And I think we said probably we want to do v's on the outside for that one because horizontal slices make most sense. All right, let's set it up. Pull that half all the way out in front. Du dv Okay, look at that picture. V runs from 1 to 2. And for each such V, U runs well, what equation is that? What is that? What's left curve? Left curve, that's V equals negative U. It's just a line on a 45. And right curve, that's V equals U. So U runs from minus V to V. And this integral is decidedly doable. Remember, that inside integral, U is varying, V is constant. So that's like integrating e to the x over 3, which is no trouble at all. Now, you may say, oh my gosh, that is a ton of work. Are you serious? These UV substitution problems are really like this? To which I respond, yeah, it's a fair bit of work, but I am telling you, if my options are to do that integral over the original region R in the original variables x and y, or do all this work to get it down to this integral, oh, I'll do UV sub all day long. That integral we have it down to is not bad. Anyway, choosing the appropriate substitutions is way trickier here because there's two variables going on. But when you do it, if you keep track of that Jacobian factor, you can trade in the old integral for hopefully something much better based on your choices for U and V. Okay, practice hard. We have Thursday and Friday to talk over these ideas. See you next time.